Hello everyone. Some questions don't test how much mathematics we know. They test how quietly we can look at them. Today's video is about three such problems what I have taken from the previous year questions asked in JEE Main. These questions are from complex number chapter. Different years, different forms, but connected by one invisible thread, the structure. At first glance, these questions look heavy. Complex numbers, real parts, locus, ratios, and whatnot. The kind of problems that invite long algebraic manipulation, and it is like punish us for choosing it. But if we pause just for a moment and ask ourselves, what is really being controlled here? Something beautiful starts to emerge. So the solution what I'm going to present to you has no unnecessary calculations, no such long mechanical steps. These solutions are very short as far as mathematics allow to make it short, but not shallow. They are elegant because they respect the problem's design. If you are preparing for JEE, this is the kind of problem or this is the kind of thinking that saves your time and builds confidence. And even if the exam is behind you, these problems still teach you how mathematics rewards clarity over unnecessary effort. So if you want to give a try to these questions, I request you to do it. Do the questions by your own so that you can feel the difference of the two kinds of methods. So let's begin. All right, so let's start doing the questions. The first question is from 2025 itself. And the question demands to find out the locus of a circle, which is defined in a complex number. And it is rated by this. And they ask for the center and the radii of the circle. And there we have to count. So you notice what the situation is here. Suppose I'm assuming this as u. You can notice that this is u bar, u conjugate. It means they're asking only for the real part of u plus real part of u conjugate, isn't it? And the real part of u and real part of u conjugate is 2. It simply means that we have to add the two real parts of the complex number versus conjugate, and the sum is 2. But notice one thing, the real part of any complex number and real parts of its conjugate are the same. It means I can write it as twice of real part of the complex number u is 2. Therefore, it turns into real part of u is equal to. Now, I have this real part of any complex number is 1. It means that the imaginary part can be anything, but the real part is certainly to be 1. So I assume that u, this complex number, as 1 plus and any beta as a parameter. Beta is any parameter or any arbitrary constant. Beta is any parameter because this beta is a constant, but you also notice that beta is a real number. When the real number attached to the iota, that will give the real imaginary part of that complex number. So when you say the real part of u is 1, the imaginary part is not known, but not known means it is a parameter or it will be arbitrary constant that will help us to decide the locus of the complex number z. So now u is 1 plus beta I. So I have assumed this as u, so let's write it there. So we get z minus 1 by 2z plus iota is equal to 1 plus bi, is beta I. And notice one thing, that we have to find the locus of z. So we need to find out the real and imaginary part of the complex number, the x and the y. And of course, the beta will be involved there to find, actually to decide the x and y. From there, we will eliminate the beta and we get the locus. So what we do here, first let me write z minus 1. And I'm multiplying this thing this side. So 2z plus iota and 1 plus beta iota. What is my plan is, I simply multiply them together and extract the complex number z in terms of something. So what I can write here, z minus 1, and then that will give you 2z plus 2z beta iota plus iota, and here we get minus beta. Now notice what will happen if I want to collect all the terms containing z together, that this will give you z. I'm taking this way, I'm bringing this z this side, right? 2z minus z, and then here I have 2z beta I, and sending everything on the left hand side, which is not the term not containing z. They'll give you beta in the positive side, minus 1 and minus I. So now I can extract the value of z. Z is equal to what? That is going to be, oh, z is equal to nothing. Z, I wanted to say z times 1 plus 2 beta iota, and that is equal to beta minus 1 minus iota. And notice one thing, that here I have to find out the x and y, the locus of z, and beta is a parameter. So if I want to find the x and y, I can immediately say that, okay, this is z here, I can write as x plus iota y and multiply with 1 plus 2 beta I. That is going to be beta minus 1. And from there, you can see this is going to be the real part, imaginary part directly. If you multiply to the left hand side, this two product, the real part will become x minus 2 beta y. Beta only, 2 beta y. And the imaginary part will come as x with 2 beta. So 2x beta I can write. And also 2 beta I, and then this will give you plus y. So beta minus 1 and minus I on the left hand side is. If you compare the real and imaginary part, we get x minus 2 beta y is equal to beta minus 1, and 2x beta plus y is equal to minus 1. So notice from here I can get the value of 2 beta, because we want to eliminate 2 beta from these two equations. Let's find out the value of 2 beta from here and substitute it in this. What I mean to say, that from here I can find the value of beta or 2 beta and substitute it in this first equation. What is the value of 2 beta here is minus of y plus 1 divided by 2x. And I'm substituting this 2 beta directly here. So it will give you x plus y plus 1 by 2x times y. But at the place of beta, I have to substitute minus of y plus 1 by, what I did, the mistake is there, that is take here that I shouldn't write. Okay. So this will give you 2 times x, because I need beta there, and minus 1. Now multiply the entire equation by 2x so that I can kill this. So it will give you 2x squared, and that is, by the way, here it will come 2 not 2 actually, x. So this will give you 2x square, and this will give you 2x times y plus 1 into y by x, and here the 2x is gone, so y minus 1 and minus 2 x. So from there what I'm getting is x cancels here. I'll give it 2x square, and also you can notice this will 2y square, then 2y, and this will give you plus y plus 2x and plus 1. So again, if you divide by 2, it will give you x square plus y square, and this 2 will become 3, so 3 by 2 y and plus x and plus 1. So to find the center, so center, that is the a coordinate, will become negative 3 by 2, negative 3 by 4 rather, and the b coordinate is minus 1 by 4, and the radius square is, this is going to be minus 3 by 4 square minus 1 by square, and minus, will give you 9 by 16 plus 1 by 16. So from there, whatever we got here, a, b, and r square, we substitute in this. A is the x coordinate. Now, a is minus 1 by 2, and this b is minus 3 by 2. Here there is no problem. So in this way you get the answer and so on. So I'm stopping here because my intention is just to show you how you can calculate easily, and this calculation, this easy calculation, do it by you. Let's go to the next question, and this question says that the set S Z belongs to complex number which has no I and no 2I in this complex number set. And why it is so, you can identify because this denominator, they don't want to make 0. And the meaning of this statement here in this bracket, this thing, is important. This tells that this whole complex number is a real number. It means if you take any complex number of such kind which has the imaginary part 13 by 11, negative 13 by 11, and real part can be anything, then if you put that kind of complex number here at the place of z, and if you evaluate it, that will give you the complex number as a real number. Means imaginary part will not be there in there. So this is the whole idea of this question. So how do we approach easily? Let's think. But before that, you see, what is the genuine, actually natural way to think that this alpha minus 13 by 11 iota is a complex number which satisfies this relation. This relation means this is a real number going to provide if you substitute like this. So one can think that, okay, why not I can substitute alpha minus 13 by 11 iota at the place of z and evaluate everything, and after that I will take the imaginary part of that complex number as 0, and from there I can find out the value of alpha. So it will take long, even you can solve it. It's actually not a incorrect method. You can solve by that way, but it take longer. So what is the shorter way to do it? Let's think here. This is actually, they've given that the complex number there is in the form of that we can factor it. So you can see that this is z plus 3 iota and z plus 5 iota are the factors on the numerator. And in denominator, of course, I and 2i is inviting us to use those things. Z minus I and z minus 2i. You see the denominator, if you multiply, you get this back because 2 iota square will give you the minus 2. So this complex number wants to be a real number, correct? this wants, why I'm writing like this. So we can just take that this belongs to real number. Now, let's assume that Z is a complex number which has some real part and some imaginary part. I'm not assuming the imaginary part 13 by 11 because our calculation will be messy. At the end, in the end result, we'll substitute 13 by 11 if we need it. So I'm assuming that that complex number, what is designed like that, is x plus iota y. Substitute there, so we get what? X plus and 3 plus y I. And here x plus 5 plus y iota. In denominator, again the similar kind of story will be there. X plus y minus 1 iota, and here x plus y minus 2 iota. Now this is a complex number we have, and this wants to be real. This is a real number. It means its imaginary part should be 0. But let's find the, how do we find the imaginary part? Of course, we have many ideas, like we've expanded numerator and denominator separately and then take the conjugate of denominator to multiply and divide. And after that, we identify the real and imaginary part of the complex number. And from there, we just make the imaginary part of that complex number equal to 0. So that I don't like because it's very inconvenient. So what we can do better, just multiply that and identify the real and imaginary part of the numerator separately and denominator separately. Yes. Okay. So what I do here, this is going to be x squared and minus 5 plus y into 3 plus y. This is the real part of the complex number in the numerator. What we get is here is x times I is a common because x times I will come from here. I just want to show, and again x times I will come from xi will get common, and if I get xi common, that will give you what? 3 plus y plus 5 plus y, right? And in denominator, again we get the similar kind of structure, x square minus y minus 1 into y minus 2. And here what I get is again xi common, and this is going to be y minus 1 plus y minus 2. If you simplify it further, this will remain as it is. So x square minus 5 plus y into 3 plus y is the real part, and imaginary part is still there, x times I, 3 plus y plus 5 plus y. Why I'm writing like this is 8 plus 2. And here again x squared minus y minus 1, y minus 2, and this is xi, and this is going to be 2y minus. Now the problem is this one. This wants to be, let me write it because every time I'm uttering it, wants to be a real number. So if it wants to be a real number, I can think that, okay, in what condition it can be a real number. So I will provide the condition for it. You can notice that if I make this thing 0 and this thing 0, because x cannot be 0, otherwise the complex number will be, z will be purely imaginary number. That is not actually allowed, I think. Z belongs to complex number and it's not a purely imaginary. So x cannot be 0. Otherwise, if you took x equal to 0, that will completely get killed, and of course we will be saved with this real part by real part. Or if x not 0, I can say that 8 plus 2y and 2y minus 3 should be 0. Both should be simultaneously 0. Of course, this will not allow us to give this kind of situation that y cannot be two kinds of thing at the same time. So this 8 plus 2y and 2y minus 3 cannot be simultaneously 0. So this plan is not working, means this cannot be 0 at the same time. The other way is that, is it possible to make these two together 0? If this will become 0, automatically the I and I will get cancelled and we are saved with the real part. How we can say that these two are actually going to be 0? But before they want to be 0, is both, these two quantities must be equal. Then only I can say they are equal to some quantity. Because this also going to be 0, at the same time denominator, this part also going to be 0. So for that, x square same. So these two must be same. Then only I can set this to be 0. It means I need to check that whether 5 plus y into 3 plus y is equal to y minus 1 into y minus 2. At what number? Because you see the complex number x plus iy is in this structure, alpha minus 13 by 11. So x is nothing but alpha. X is alpha, but y is minus 13 by 11. So is it equal? The both sides are equal. When I substitute y is equal to minus 13 by 11, let's check it. So here I will get 5 minus 13 by 11. And here I get 3 minus 13 by 11. And this side I have minus 13 by 11 minus 1, minus 13 by 11 minus 2. And we compare, we just calculate left hand side, right hand side, one by, like separately, and we see that both are equal or not at the same point. This is going to be what? 11 5 is 55 minus 13. And here 33 minus 13. And this side, what is that? 11, 13 into 13 plus 11, because minus and I can manage. And here also 13 plus 22. And from there, this is 55 minus 13. That is going to be how much? 42, sorry. And this is 20. And here I have 13 and 11, 24. And it's going to be 20. You notice they are equal because this is going to be 7 into 6 into 20. And this is going to be also, this is 7 into 5, and this is 6 into 4. So 4 into 5 is 20. So again 7 into 4 into. So in this way we can see that they are equal. And so y is equal to minus 13 by 11 will work. For that, they're equal. It means what? Our plan to make this real works when these two quantities are equal. And if two quantities are equal, it means I have x square is equal to this thing is equal to 0. It means x square minus this thing is equal to 0. It means x square is equal to 5 plus y into 3 plus y. It means we got alpha square is equal to 5 plus y into 3 plus y on what number? On this number at minus 13 by 11. And minus 13 by 11 we have already found here. That was going to be 840. Really? 840. So 242 into alpha. Really sorry. There's one problem here. I made one mistake here. There's the x square is, this is going to be 11 into 11 because here it got cancelled, but denominator here will get 1. Now we substitute this thing there, and of course this 242 is given to get cancelled by 121, and from there we can find the answer. So that is a way we can think smartly like it, and then we can solve. Now the last question, third question, this one. We have a question here that z minus z bar plus zz bar by 2 minus 3z plus 5z bar, and z belongs to complex number, of course, and z is 3. So real part of z is already given 3 here, and it says that the set is this complex number completely lies in the interval of alpha to beta. So what we can do to actually find it out, the interval for the real part of this alpha to beta, and then we find out beta minus alpha. So here they have given z minus z bar. So z I am assuming as 3 plus bi. So z bar I have 3 minus bi, and if you take z minus z bar, you know that is actually twice of bi, because 3 and 3 will get cancelled. Zz bar is nothing but mod z square, that is going to be 9 plus b square. So we'll substitute everything there. So I have this is 2b iota plus 9 plus b square, and divided by, this is twice of minus 3z plus 5z. So let's calculate it. Minus 3z means 3 plus b iota, and 5z bar means 5 times 3 minus b iota. In denominator we cannot do anything, we have to simplify it as it is. So it is 9 plus b squared plus 2b iota, and here I can collect all the terms containing a real part and also imaginary part together. This is going to be 3z, so I did a mistake here. That is going to be 3 times. So that is going to be what? Twice of minus 9 minus 3bi plus 15 minus 5bi. 9 plus b squared plus 2b iota, and here divided by 15 or 2. 17 minus 9 is 8, and minus 8. So that's not so difficult to calculate. Here I left b, 8bi. Okay. Now I have to multiply and divide by the conjugate of it. So how am I multiplying it? Let's see. It's 9 plus b square, 2b iota, and divided by this 8 common. So I get 1 minus b iota. I multiply and divide by only 1 plus b iota and divide by the same conjugate. So here I need to find out the real part of this complex number only, on which we have to work on, that how in what interval that real part will lie. I'm taking only the r, the real part, so it will give you 9 plus b square and minus 2b square. In denominator I have 8 is out and 1 plus b square. We'll get 9 minus b square by 8 times 1. Now there are different ways to find out the interval for r. One way is that, so I will give you 2 methods. One, you can write the r in terms of 1 plus b square in the top. So I can write here 10 minus 1 plus b square and divided by 8 times 1 plus b square. From there I can write 10 by 8, 1 plus b square, and minus 1 by 8. And from there we have to work on only b square. You notice that if I have to find out the maximum value of r, we get when this value will become minimum, because When this is minimum, then this whole thing is maximum, and from that maximum you are subtracting something, so you'll get the maximum difference. So the R max, we can write it or find it when at b is equal to 0, because this is the minimum value of the b square. So we get it what? R max is 10 by 8 minus 1 by 8, that is 2 by 8, sorry, 9 by 8, and R max. So that is the value of the beta value. And when this will be minimum, you see, when this will become very low, like, so this b square should be very high, and the highest value of the b square is infinity. So R max, I can say, will happen when b tends to infinity. So when b tends to infinity, R max, R min, and here also R min, that is going to be 0, this is the whole thing will going to be 0, and we'll get the minus 1 by 8. And notice that this will not be the exact value because we are taking the b approaching towards infinity. So that is going to be minus 1 by 8 open bracket. So alpha is minus 1 by 8 and beta is 9 by 8. We have to find out the difference of beta minus alpha and multiply by 24. So you can. The other way to do from here is this one, that I had R is equal to, where that the original one, okay, 9 minus b square divided by 8 times 1 plus b square. Now what I can say that, let's say this is x, and the idea is that, can we find the minimum and maximum value of x? Yes, we can find. So let's extract the value of b square, and in terms of x, what you can write? 8x plus 8x b square is equal to 9 minus b square. So write all the terms containing b square together in one side. So it'll give you 8x plus 1 b square is equal to 9 minus 8x. So we get here b square is 9 minus 8x divided by 8x plus 1. And you know that the b square is always positive. So this ratio should be positive. So I will have a number line which is giving the numerator and denominator zeros. So that is going to be minus 1 by 8 and this is 9 by 8. You notice how to use the sign diagram. So minus 1 by 8 will be open because in denominator, 9 by 8 is closed because 0 is included. And in this interval only that will become positive value. So that's why we are taking minus 1 by 8 to 9 by 8 as the value of x, which is in turn the value of r. So this is the way I discuss these questions in my class. And I found that many students are like doing, I'm not saying they are doing wrong, there's a different thought process, and they all are doing with some rather longer calculation. In this particular last questions also, they have done many longer calculations all. By the way, this kind of questions we have done in functions also, like how to find the range and all. So that is coming from that. Particularly this question, this one, second one already discussed. To identify the real number means how it turn into the real part or the real number only. This is challenging. But anyway, I hope you liked it, and see you in the next video with some other such concepts and calculation tricks. Till then, stay math active.